This is a lab where Kubernetes load balancer services become real BGP routes. A 4-router eBGP ring is built in GNS3 on Cisco IOSv with a single node K3s cluster peering into it as its own autonomous system, and with MetalLB in BGP mode announcing every service as a /32 host route. In the next 20 minutes, you'll watch the ring come up, watch the cluster peer in, watch a service VIP propagate around the ring, and then watch me kill an uplink while traffic keeps flowing. Here's the problem this lab solves. On a cloud provider, you create a service with type LoadBalancer, and the cloud hands you an IP. On bare metal, there is nothing behind that API. The service sits in pending forever. K3s papers over this with its own built-in load balancer, service LB, but that just binds host ports and hands out the node's own IP. It doesn't give you a dedicated address it can advertise to the rest of your network. MetalLB in BGP mode fixes this properly. The cluster becomes a router from the network's point of view. It speaks eBGP to the upstream devices and advertises each service IP as a /32 host route. The question I wanted to answer with this lab: does that hold up in a real routed topology? Not a flat switch domain, with multiple autonomous systems, path selection, and failover when a link dies. Here we have the topology. We have 4 routers, R1 through R4, each in its own autonomous system, 65001 through 65004. They form a ring over /29 transit links, 10010/29 between R1 and R2, then 10020, 10030, and 10040, closing the loop back to R1. The K3s node attaches to the ring twice. One uplink to R1 on 10050/29, one to R4 on 10060/29. MetalLB runs on the node as AS65100 and opens one eBGP session to each of those 2 routers. R2 and R3 never peer with the cluster. They only learn service routes the way any BGP network learns anything: propagation around the ring. 2 more pieces. The service pool is 172.1.6, 10.0/24, so every VIP lands in that range. And there's a test client behind R3 on 10.0/70/29. It does not run BGP. It exists purely to originate traffic that actually crosses the ring, and later on I will explain why that matters more than it looks. Here we have the full peering design. 6 eBGP sessions total, 4 around the ring, 1 per adjacency, and 2 from MetalLB, 10055 to R1 and 10065 to R4. Each BGP peer, object in Kubernetes, pins its source address so the speaker originates each TCP session from the correct interface. With 2 uplinks on the same host, that detail is not optional. The design gives the ring a property worth watching for. R3 hears about the cluster from both directions at unequal distance. 2 AS hops through R4, 3 the long way through R2 and R1. That asymmetry is what makes the path selection and failover demos meaningful. Here's the run order, which is the same order the repos deploy script uses. Host networking, a router bootstrap, Ansible pushes the ring config, K3s and MetalLB install, then the MetalLB BGP objects, then the two demo services. Once everything is up, I'll trace one VIP through the router's BGP tables, prove traffic reaches the pods from outside, and then start breaking links. Let's go to the terminal. First, we have the host plumbing. GNS3 connects the emulated routers to the real host through tap interfaces, so this script creates 3 of them. Tap 0 is management, 192.168.0.100. Tap 1 and 2 are the 2 cluster uplinks located at 10.0.5.5 and 10.0.6.5. It also installs return routes into the ring, primarily via R1 at metric 100, backup via R4 at metric 200, and it also sets loose reverse path filtering on the transit taps because during failover traffic can arrive on one uplink while replies leave on the other, and strict RP filter would drop those packets at the interface. The RP filter setting will bite you if it slips. A reboot or a partial rerun quietly resets it to strict, and the symptom is quite maddening. So now we're moving on to the second script. The second script builds the test client, an isolated network namespace branched out through tap 3 to R3. One thing that will bite you here, each tap has to be bound to its cloud node inside GNS3, and the taps do not survive a reboot. If tap 0 isn't bound to cloud 1, the management plane is just silently dead. Pings to the router management IPs go nowhere, and every Ansible play fails at connect. So before we go any further, we are going to go in here into GNS3, and we are going to delete the wiring between the cloud nodes and the routers. And then we are going to rewire them to make sure that they are working correctly. Cloud 1 is going to be bound to tap 0 and to switch 1. Cloud 2 is going to be bound to tap 1 and to R1 E5, which will be named G05 on the router itself. Cloud 3 is going to be bound to tap 2 and then to E5 on R4, which once again will be named G05 on R4. Before we can confirm connectivity between the tap interfaces and the routers located inside the ring, we first have to run the bootstraps router script. The routers boot with blank configurations, so before Ansible can SSH in, something has to get SSH onto them. This script talks to each router's console port through the GNS3 API and runs a small expect loop. It waits for boot, it declines the initial config dialog, and then it pastes the bootstrap. Hostname, credentials, SSH on the VTY lines, and management address on G04. Watch it walk R1 through R4. And if we check this, we can actually see the script working. And now we'll check the terminal, and the script has executed successfully. This is the only console interaction in the whole lab. Everything from this point forward is code. Mark. Now the real configuration. 2 Jinja 2 templates rendered per router from host vars. The first sets interface addressing and descriptions. The second builds the BGP stanza, router BGP with the local AS, each neighbor with its remote AS, and the network statements under the IPv4 address family. R1's host vars, for example, declares neighbors 10.0.1.2 for R2, 10.0.4.4 for R4, and 10.0.5.5 for the MetalLB session that doesn't exist yet. The config is declared now. The session comes up when the cluster does. Mark. And the verification is a playbook too, not eyeballing. It asserts every ring neighbor is in established state and runs loopback to loopback pings across the ring. Everything looks good. The ring is now converged. Now we're going to take a quick look from the router's seat before we add Kubernetes. R1 shows 3 neighbors. R2 and R4 are established with prefixes flowing. The transit subnets and the router loopbacks. No 172.1.6 anything yet. But if we look at the third row, 10.0.5.5 and AS 65100, and where the others show a prefix count, this one shows a state, idle. That's the MetalLB session. Ansible declared it back in the deploy, so R1 is already trying to open the session, but there's no speaker on the other end yet, so it never gets past idle. Remember that row. In a few minutes, the state flips to established. Cluster time. 2 flags in this install matter more than everything else combined. Disable service LB and disable traffic. Service LB is K3S's built-in load balancer implementation, and if you leave it on, it claims every load balancer service before MetalLB gets a chance. Why are we using K3S at all? That's a certified Kubernetes distribution in a single host process. That's what lets the MetalLB speaker peer straight off the host's tap interfaces, and it leaves RAM for 4 IOSv routers on the same box. Aside from Service LB, which we just disabled, nothing in this lab is K3S specific. This script also handles a race worth knowing about. K3S's systemd unit returns before the API server is actually serving, so a native kube control wait fires into an empty cluster and fails. This polls until the node object exists first. Here's the entire MetalLB BGP configuration. 4 objects, an IP address pool, handing out 172.168.10.0/24. A BGP advertisement referencing that pool. Because the default aggregation length is 32, every service is announced as an individual host route which is exactly what you want the routers to see. Then two BGP peer objects, my ASN 65100, the peer ASN at 10051 for R1, the peer 65004 at 10064 for R4, and each has explicit source address so that the session leaves through the right tap. Okay, so apply it. Kube control confirms four objects created, the pull, the advertisement, and both BGP peer objects. The speaker reads the peers and opens a session out of each uplink, and R1's 10055 row flips from idle to established. And we can confirm that by issuing show IP BGP summary on R1. And as you can see, 10055 is present, and the state and prefixes received is at 0. Two demo services, Who Am I, is a 2 replica HTTP echo that reports which pod answered, pinned to 172.168.10.10 through the MetalLB.io LoadBalancer IPs annotation. NGINX hello is a single replica pinned to .20, there to show multiple independent /32s from the same pool. Both services show their external IPs. On a cloud provider, you'd shrug at this. On bare metal, this is the whole trick. These addresses only mean something because BGP is about to make them mean something. So let's find that service in the network. R3 is an interesting vantage point because it never peers with the cluster. Everything it knows arrived by propagation. Two paths for the Who Am I VIP. One learned from R2 with AS path 65002, 65001, 65100. 3 hops the long way around. One learned from R4 with path 65004, 65100. 2 hops. BGP picks the shorter AS path, so the best is via R4, with the next hop of 10034. Kubernetes service annotation just became a routing decision on a Cisco router 2 autonomous systems away. That line is the entire lab in one output. Same story from the cluster side inside the speaker's FRR instance. Both uplink sessions are established and prefixes have been sent. 1 per service. Prefixes received 0, and that's by design. MetalLB rejects everything inbound by policy. It announces services, it never installs routes on the node. Now we're going to check to see if the traffic actually has flown. Notice that I'm running curl inside that client namespace behind R3, not on the node. This matters. Kube proxy hooks load balancer VIPs into the NAT output chain, so a curl run on the K3S host does get denatted straight to the pod before a routing decision ever happens. This succeeds with BGP completely down, and it proves nothing. The namespace client's traffic enters the topology at R3 and follows BGP best path across the ring like a real external user. So look at the responses. We have 2 curls to the same VIP with 2 different pod host names. The Kube proxy balancing across both Who Am I replicas behind one BGP advertised address. The 20 VIP answers 2. Failover. This loop hits the VIP once a second from the client behind R3 and prints whichever pod answered. 2 facts set up what you're about to see. The client's traffic enters the ring at R3 and R3's best path to the VIP is through R4. R4, in turn, reaches the VIP over its own direct session to the cluster, the one we brought up a few minutes ago. That direct session is what I am going to kill. So we're going over to R4, and we're going to interface G05. We are going to shut down this interface. That is R4's cluster uplink. Shutting it drops the MetalLB session on R4 immediately, fast external failover, and R4 withdraws the VIP route it was originating from that session. If we take a look at the loop, it keeps printing host names. No gap. Here's why, and it's worth being precise about who sees what. Watch the two different vantage points. From R3's seat, nothing appears to happen. Its best path to the VIP through R4 before, and is still through R4 now. The next hop doesn't move. The only change R3 sees is the AS path quietly getting one longer, to 65004, 65001, and 65100, after the advertisement interval. If R3 were your only window, you'd barely notice an outage occurred. The real action is one hop downstream at R4. R4 just lost its direct road to the cluster, so it promotes the backup it was already holding, the path to the VIP the long way around the ring through R1. R4 kept that route in its table as non-best the whole time, so the instant the direct session died, its best path calculation reran and picked it up with no gap in coverage. Physically, client traffic now runs R3 to R4 to R1 into the node's other uplink. R3 still hands every packet to R4 exactly like before. R4 just forwards it to a different direction. When I ran this for the repo captures, the loop never missed a single probe at the specified 1 second resolution. We're now going back over to R4, and we are going to bring the link back up. The direct session reestablishes, R4 prefers it again, and R3's path shortens back to the 2-hop 65004, 65100. One honesty check before I move on. In the repo captures, I also shut R1's cluster uplink, while R4's was still down, cutting the last path to the node. The loop printed fail lines instantly. That matters because a test that can't fail proves nothing. This one fails when the path is truly gone, so every passing probe in between actually means something. Everything I just showed by hand is also asserted in code. This playbook, Ansible playbook, verify K8s routes.yml, checks both MetalLB sessions are established on R1 and R4 directly. It checks the service routes exist in every router's BGP table, and checks the whoami/32 carries AS65100 in its path. It also collects each router's BGP and routing table entries for the pool along the way, so a failed assert arrives with the state you need to debug it. And it asserts the sessions themselves rather than inferring health from downstream routes, because as we just saw, downstream route state barely moves during a failure. What this lab demonstrates concretely: eBGP design across 5 autonomous systems with deliberate asymmetry to make path selection observable. Kubernetes networking below the service abstraction, MetalLB, kube proxies DNAT behavior, and why test methodology matters as much as the test. Automation end-to-end, Ansible with Jinja 2 templates for config, playbooks that assert instead of display, a Python console bootstrap over the GNS3 API, and a stage deploy script that resumes from any failure point. And validation as a first-class concern. The strongest evidence in the repo is a failure capture proving the test can detect a real outage. Everything is in the repo. The GNS3 project, all router configs and templates, the Kubernetes manifest, and both README files. Link on screen and in the description. One pointer before I close. This 4-router ring isn't unique to this lab. is the same topology as the sibling BGP Grafana monitoring lab in the repo. So if this run interested you, that one shows what else this ring can carry. If routed Kubernetes on bare metal is your kind of problem, the repo is the best place to start. Thanks for watching.